So we'll start the competition by asking you to introduce yourselves.
Okay. I'm Guy Blanc.
I'm Jenny.
I'm Michael On.
Hi, I'm Sandeep Solo.
Evan Liang.
Right, welcome. You may begin.
All right, good morning, everyone. Today we are here to talk about what higher education is really worth. And so everyone knows that college is expensive and that this dollar really isn't going to cut it anymore. And so today we will be showcasing a tool that we developed to help current high school students make a more informed decision about their higher education decision. And so our tool is threefold. First, we created a more accurate method for calculating the cost of college. And then we will discuss the benefits of pursuing various degree options. And then lastly, we will touch upon a few more qualitative factors in making the decision, such as job satisfaction and quality of life. And so to help us create a more accurate method for calculating the cost of higher education, we need to make a few key assumptions and simplifications. So we assume that parent age, student income and parent assets distribution were all constant. The reason behind this was that we found that these variables did not significantly alter our model, and so it was simpler to just keep them as constants. We then broke the cost of college down into four different variables. And so the first one is the expected family contribution, or how much your family is expected to pay towards the college tuition. And so this mainly depends on the family income and also on family assets. Secondly, we looked at the remaining cost of the college tuition, which is covered by the college and by the federal government. And so we found that about 80% of this remaining money is in the form of loans, and 20% of it is in the form of grants. And so the 80% that is in loans has to be repaid back at some point in time, and therefore also factors into the cost of college. Thirdly, we looked at the rising cost of college. So a College Board study found that the cost of college has been increasing by a rate of about 10% every 5 years. And so we added that to our cost factor as well. And lastly, we looked at the opportunity cost of not being able to work a full-time job while attending college. And so putting all this together, we get our formula for the average yearly cost of college. If we let P be the initial college tuition, after adjusting for inflation and for the rising cost of college, the average yearly cost is actually about 3% higher. And then we broke down college tuition into the expected family contribution and also the amount that's given to you by the federal government and by the college. And so we omitted the 20% that is in grants because those don't have to be paid back, and we kept the 80% that is in the form of loans. And lastly, we calculated that the average high school graduate that works a full-time job makes on average $16,000 a year more than the college student who may or may not be working a part-time job. And so here are results for four-year public institutions. As you can see, for a family whose income is $35,000 and a family whose income is $125,000, there's only about a $2,000 to $3,000 difference in what our cost of college was. And so the reason behind this is while the expected family contribution may be drastically different, the remaining money that's given by the college and by the federal government, most of that has to be repaid at some point in time. And therefore, that factors into our cost of college. You can see the same phenomena in our results for four-year private institutions, where a $90,000 difference in family income results in only a $5,000 to $6,000 difference in the cost of college. You can also see that for children whose family income is $35,000, the cost of college is pretty high, $40,000. And so the reason behind this is because we factor in the opportunity cost of not being able to work during college, and that contributes $16,000 every year to our cost of college. And so what this means for our model is that the largest determinant in whether one should or should not pursue a higher education is whether one can afford not having a full-time job right after college. And so what this also means is that President Obama's recent suggestion of implementing 2 years of free community college for all high school graduates doesn't significantly affect our model. So the people that require the income provided by a full-time job will still have to enter the workforce because they're not getting money from this program. However, for those of you that that are more on the fence about higher education, this initiative may be the push that they need to pursue higher education. And now we will go to Sandeep Sowal with part 2 of our problem.
So in part 1 of the model, we looked at the true cost of college. But in part 2 of the model, we will look at the different financial suitability of the different career choices that you can have while at college. So every graduate with a degree can exist in 2 states. Either they're employed or unemployed. Furthermore, after every time step of 1 month, every graduate can change their state or stay in the same state. So we let P be the probability that an employed graduate will stay employed in the next month. And we let Q be the probability that an unemployed graduate will stay unemployed in the next month. The diagram here shows the relationships between employed and unemployed. Now we reason that P, the probability that you stay employed if you're employed, should depend on the job experience that you have. So therefore, P should be a logistic function of E. Now Q, the probability that you'll be unemployed when you're unemployed in the next month, we let that be constant to simplify calculations. Furthermore, we reason that in the short time period, the fact that you're unemployed should not affect the probability of you being hired in the next month in the short term. Our initial conditions were that every graduate is initially unemployed. Now to find the probability that a graduate is employed or unemployed at a time step t, we look at the probability that the graduate is employed or unemployed in the previous time step, and we multiply it by the corresponding transition matrix, which just allows us to change states. Then we looked at real-world data about the percentages of graduates that were employed in various fields over different time periods to find the values for our constants P and Q. Well, P is not a constant, but the constants in the function. So we found that these constants best fit the actual real-world data. Then to implement this model, we made a Python program. In the Python program, every graduate has certain unique characteristics. So every graduate is either employed or unemployed. They have their own unique months of experience, their current salary, and the amount of money that they have right now. Now, Michael will talk about some of the results of the program.
Okay, so in our Python program, we simulated 1,000 employees with 2 years associates, 4-year non-STEM, or 4-year STEM degrees. And so basically, we modeled them over a 20-year period and measured how much they would earn relative to an average high school graduate. So in these graphs, the horizontal axis represents the time in months since graduation, while the vertical axis represents the amount that the graduates earn relative to the average high school graduate. So in each graph, there are green and red regions. The green indicates that a graduate has earned more than the typical high school graduate, while red represents the cases where the graduate has earned less than the average high school graduate. So then we calculated the median time for these graduates to basically break even with their high school graduate counterparts. And we found that the median time was actually the greatest for the 4-year non-STEM case. And this is because of the college and opportunity costs associated with 4 years of higher education rather than just 2 in the 2-year associate case. However, after the 20-year period that we modeled, a higher percentage of 4-year non-STEM graduates ended up earning more than the average high school graduate relative to the 2-year associate case. Finally, the 4-year STEM graduates required the least median time to surpass their high school graduates. And in fact, all 1,000 of the simulated employees ended up earning more than the average high school graduate after the 20 years. Then we did a sensitivity analysis of the model. So what we did is we varied the amount of debt that a STEM graduate would have after 4 years of college. And this stems from both the cost of college as well as the opportunity costs. So we measured the median time for these STEM graduates to surpass their high school counterparts. What we found was that an increase in the STEM graduate debt led to a roughly proportional increase in the median time for these STEM graduates to earn more than the average high schooler. And as you can see from the graphs, an increase in the STEM graduate debt does not significantly alter the shape of the graph. And in fact, in each of these 3 scenarios, all 1,000 of the simulated employees still ended up earning more than the average high school graduate. And now Jenny will introduce the final part of our model.
So in part 3 of the problem, we were asked to kind of devise a personalized tool to help high school seniors determine what is the best college decision and therefore resulting life path, which includes things beyond just the immediate financial outcome of what you're going to major in college. And so what are some of these quality of life factors that will affect your happiness after graduation? Some of the things we looked at were, do you feel like your boss is giving you enough independence or responsibility in your job? Are you satisfied with your job benefits and location? Even things like, do you feel like you're challenged at work every day and that you're contributing positively to society? And so the tool that we devised is really twofold. First, what we did is we would ask the high school senior to calculate if it's even economically feasible to go to college based on the college costs that we devised in part 1, and then have them find out what their projected salary and time to pay off their college debt would be using the seating Markov chain model that we created in part 2. And then finally, we would have them rank all of these 8 job satisfaction or quality of life happiness factors, along with the 2 salary factors, and then multiply the corresponding values and weight them using this National Science Foundation survey of over 200,000 male and female professionals who reported on the job satisfaction of their respective fields. And then finally, come up with a quantitative metric so that you can see how happy you would be in each of these different fields after you graduate. And so next, Guy will talk about some of the strengths and weaknesses of our model.
Okay, so it is important to note some of the weaknesses that may be present in our model. One thing we do is we assume that hirings and firings happen only at monthly intervals. In the real world, this may not be the case. A person can be hired or fired at any given moment of time. We had to make this assumption to make it computationally feasible to calculate our model in the given time period. Another assumption we made is that the availability of jobs does not significantly change over time. Essentially, we looked at current market data and applied it to the future. We did this because future market data is very difficult to find and unpredictable, and anything we could find was not enough to calculate all of the constants we needed for our model. We also assume that as experience increases, so does the probability that an employee retains their job. In most cases, this assumption increases accuracy. However, an IEEE study found that in some cases, such as IT, this may not be the case. In some industries, knowledge of cutting-edge technology is seen as very important, and older, more experienced graduates or employees may be seen as having less of this knowledge, making it more difficult for them to retain their job. Our model also had many important strengths. We were able to make a survey including not only financial factors such as salary, but factors that contribute to an overall sense of well-being such as opportunity to contribute to society in one personalized quantitative metric through our survey. We also derived all our constants from real-world data, ensuring that our model is consistent and accurate with what you will see in the real world. Lastly, and perhaps most importantly, our model was very flexible. Because of its nature, we were able to incorporate personal experience into a career path. Also, because of its iterative computational nature, we were able to seed 1,000 employees, making it so we didn't collapse our model into one single average career path, but instead able to visualize a wide variety of career paths. We would like to thank our teachers, Dr. Teague and Ms. Belladin, and the Moody Foundation and SIAM for this wonderful competition. Here are some selected references. Thank you for your time. Do you have any questions?
I'll start. In the section 2, you use simulation of a Markov chain to evaluate the model, and simulation is a very powerful tool. Can you give me some guidelines as to how long do you run the simulation, either theoretical or empirical guidelines, because this is a challenging problem often, to understand, do you converge?
Okay, are you talking about computational time or a period of time?
How many simulations should you run?
So we had 1,000 employees for each simulation, and we ran it 2 or 3 times for each case to make sure what we were seeing was consistent between them. And we found that it looked pretty much the same. You see in the middle a large chunk of employees, and then on the edges you see a few lines that might vary between each of the runs, a few of the outliers, but what you see is pretty much the same. And each one included 1,000 employees, so we tested a few times and it was very robust.
So in your presentation, you alluded to the fact that when students take out loans or need to pay for college, somehow the whole 80-20 rule that they would need to somehow pay that back, but it wasn't so clear to us in your model where those payment plans were fitting in. So could you go back and show us how the repayment of the loans fits into the model, and then how that repayment affected your conclusions?
Okay. So as Evan talked in part one, we incorporated into the original debt. So essentially, for our model, we had an original debt that each employee had. Now, what we did is if you were below zero in the model at any time, essentially we added, I think it was 3% fixed interest on whatever your loan was. So if an employee stays below zero in the red zone for a long period of time, it becomes more difficult for them to make enough money to get back. So that proved to be fairly effective.
So is in one of your original equations, you had a 1.03p? So are we seeing no compounding? Or explain that to me.
That's actually something different, because we said that we calculated the rising cost of college as well. So that's actually the 3% increasing average college tuition over the 4 years. And so if you start with like P as the initial cost of college right after graduating, the actual average cost is 3% higher, which is the 1.03.
Okay, so that's just the fixed.
Yeah, that's different from.
And then your 3%, is that being compounded somehow? Your interest 3%?
That's in the Python program itself. So so the 3% increase is an average of increased cost over the 4 years you're in college, and then every year after that, any debt you have increases by 3%, or less than that per month, but the equivalent amount every time for every iteration of the model.
Monthly. Okay.
So I have a brief question for you, I think, or something, a consideration. I'm just wondering if a student, there's lots of personalization within your model. So if they have a chosen major or career choice, or something that spits out a certain thing, is there any way to, how would you factor in their ability or the probability of them actually completing or having success in completing the degree of choice?
So we realized that as we were devising our overall quantitative personalized metric in part 3, so we implemented an additional factor, B of bias, that we discussed in our paper, so that if you are specifically leaning towards one field over the other, you would be able to factor in your personal interests as well in the field.
A lot of students change their majors. That ought to make some changes in your model. How do you think that would affect it?
Okay, so we give you a quantitative metric, but that's a tool, it's a guideline. So essentially it's pretty much impossible for us to come up with any one number that says this is absolutely what you should do with any number of questions. It's just one tool. So we make a suggestion, and you need to compare it to what you believe is right. And throughout your degree, you might change. You might realize that what you thought was right isn't in fact right for you. So that's something that we didn't feel was possible for us to consider changing drastically over your year in college. But they could retake our survey and see how perhaps they have changed, or if they believe our tool is perhaps not the only thing they want to consider. They find that one sort of degree option and our tool is slightly higher, but they really are passionate about another subject. They should absolutely pursue it. So it's a tool. It's not this is the line and you need to follow it.
Thank you.
You want to go one more? Sure.
So I recall you talking about the probabilities in the Markov process, and you mentioned that in particular unemployment rate would not be affected by how long you have been unemployed, and certainly that probably would take we would want to take that into effect, and certainly if you had more time, maybe that's one of the things you would change. But I'm interested to know, among all of your work, what would you change at this point, and what do you think would have the most impact on your results?
So if we had more time and more computational power, I would definitely like to make Q not a constant, so a function like P that incorporates the job experience you have and also the time that you've been unemployed. But our reasoning was that, okay, so if you've been unemployed for 4 or 5 months, your knowledge isn't very outdated. So the fact that you'll be employed next month shouldn't change very much.
And one more thing that we really hoped we could incorporate, but it was more not really having the time but the data, is probability of raises and promotions. So because our model is iterative, it's very possible to say you have this % of having a raise based on your time and stuff. But it was very difficult. Perhaps it exists, but we couldn't find it. Enough data to come up with constants and models for the probability of promotions and raises. So I believe that's something that could have greatly increased the accuracy, but because we didn't have the data, we didn't want to just throw something out there.
Thank you.
Thank you.